Okay, so how to find the parameters? Overall, the parameters I've here called them W. The idea is to do gradient descent, so I want to find some updated parameters W new by starting from my previous parameters W old, and now I'm changing them by computing the gradient of my loss L. So I compute the gradient of my loss L with respect to some parameter W evaluated at the position of the old parameters. I'm multiplying this with some magic step size mu. And so I do gradient descent to get my new parameters. Now, there's much more to say about the magic step size and how to adjust this over time and so on. If we want to use all samples or only a few samples to evaluate the loss. But for now, let's just look at this the naive way. Then I need the following ingredients. I have some input X. For each input in my training set, I have in a classification problem a ground truth category, or in a regression problem some ground truth scalar number associated with that input. And if I do work in classification, then it is convenient to express the ground truth class in terms of a one hot indicator vector. So this has a 1 at the entry of the true class and 0 for all other classes. And then we need a loss function. And again, for regression, it is a good idea to use a squared loss, but when you use classification, then usually it's recommended to use cross entropy, which is defined here. So for a given input, my target T is a vector with capital K entries when I have capital K classes. The output of my network is also a vector. So I have one output neuron for each of the capital K possible classes. And I'm just looking at these outputs, and ideally, if my sample is truly of class 5, then the fifth of my output neurons should have a large response and the other neurons should have a small response. And the discrepancy is measured here with this vector, with this inner product between my target T and the natural logarithm taken element-wise of my network output O2. Okay, so overall, I get for each input a scalar loss, which I want to make as small as possible. Then I need a specification of the architecture. And for a network with a single hidden layer, and for two possible classes, I've given the architecture here. This time the input is ingested from the right-hand side, not from the left-hand side, because it's more convenient for me the way I described the equations to match this to the plot, to have the input injected on the right-hand side. Then these are again, the circles on the right-hand side are again symbols for my perceptrons. If I wanted, I could extra connections here for the bias of each of these perceptrons. I'm calling the input X. Then I have this linear operation. So the weighted sum of the inputs, which I can write as a matrix vector product here. And I'm calling this intermediate result Z1. I am then passing this intermediate result through the nonlinearity. In this case, the rectifying linear unit is used. So the rectifying linear unit can be written as the maximum of 0 and the input. And this new intermediate result, I'm calling it O1 for output of the first layer. And this intermediate result is then passed through another linear transformation and gives me a new intermediate representation Z2, which is then passed through another nonlinearity. in this case, so-called softmax, and then that gives me my final estimate of my neural network encoded in the vector O2, 2 for output of this second layer. And the softmax is defined here. So when z is a vector, I can take it, I can exponentiate it element-wise and normalize the whole thing. And like the name says, it's a softmax. It's a soft approximation to the argmax operator. Okay, so I have been explicit here in specifying my particular network, and I can alternatively write my loss as follows. So I have the loss L between my target and, here was my input, this was the linear transformation. R of the linear transformation means here I've used the rectifying linear unit. I've used the result and subjected it to another linear transformation, and finally I've taken the softmax of it. So my entire network, I have here written it as a set of nested functions, and I'm now comparing my ground truth with this function of x. So I could have written, and that's what's written on the right-hand side, I'm computing the loss between my ground truth target t and my function, which I've here called NN for neural network, which has some input x and depends on parameters W1 and W2. Now to do the gradient descent, I want to find this derivative of my loss with respect to these different sets of parameters, W1 and W2. And this is a set of nested functions, and if I want to differentiate here with respect to W1, for instance, I need to apply the chain rule. Okay, so brief reminder of chain rule, especially when we're working with vectors and matrices. If both y and x are vectors, then it makes sense to use the so-called numerator layout. So if my numerator has m rows, has m entries, then I will have m rows. And if my denominator has n entries, then I will have n columns. And compiled in this matrix, or collected in this matrix, are all these partial derivatives of the mth element of my numerator with respect to the nth element of my denominator. And the reason why this particular layout is being used here is because when I now need to use the chain rule, then I can simply multiply these kinds of matrices, which are also called Jacobians. So if y is a function of z, which is a function of x, then I can write here the derivative of dy with respect to x as dy with respect to z, dz with respect to x, and I can simply multiply these corresponding matrices. And you can verify that if we do use this numerator layout, then the dimensions will match, and otherwise we would get a mismatch. You can also use the same rules to figure out what happens when you take the derivative here of a linear transformation, like this or like that. And we need to remember that when we have a product, that we then get a sum of terms, the sum rule. Good, and this is really all we need, as long as we don't try to do too many things at once. Yeah? So if somebody asked you to differentiate this loss with respect to W1, you would usually try and do several steps together so as to avoid, writing down 3 pages of equations. But actually, even when you really have to make sure you don't make any errors, that it makes sense to break this down into really simple operations. And especially if you want to do this programmatically, so differentiate using the machine and not differentiating using your brain, then it is helpful to break these down into the simplest possible operations. Yeah? So into single, let's say, atomic operations that always accept a few inputs and produce one output. And all these atomic operations can be expressed in a computational graph. So for the network above, here is the complete computational graph. On the very left, I have the loss, and on the very right, I have all the inputs, namely my input x, my desired output t, the target, and the parameters w1 and w2. Now, in most cases, I'm not interested in a derivative with respect to the target because the target is just given. Also, in most cases, I'm not interested in the derivative with respect to the input because the input is also fixed. But usually, you are interested in the derivatives with respect to the parameters, w1 and w2. There is one exception to what I've just said, namely, there have been a bunch of papers where people try to figure out how to trick a neural network. Yeah, so let's say I am presenting the network an image of a bus, and I'm asking for what are the minimal changes in the image that I need to make the network believe that this is a penguin. And in this case, I'm taking the derivative with respect to the input x. And by the way, neural networks are fairly easy to trick, or at least the first generation ones. It's enough to make really imperceptible changes, so you don't even see the difference between the original image and the manipulated image. But the original image is correctly classified as bus, and the manipulated image is then, which looks identical to us, is then classified as penguin. And then there is another line of research that tries and make the networks robust to such modifications. Okay, but in general, we are only interested in the derivatives with respect to the parameters. And let's see if we can understand this mapping of our function above to this computational graph. So we had here W1 transpose X, which is, which is this part here. You see W1, you see X, and then I've shown a bra and a cat in this box to say that as an operation, I mean to do a matrix vector multiplication here. Then I get my intermediate output Z1, which I represent as a node in my computational graph. This output Z1 is fed into another function. So here we have, I pass it into a rectifying linear unit, and corresponds to this part of the graph. Then I get an output O1, and this output O1 I'm now multiplying with my parameters W2, which in my network corresponds to this part, and so on. And the innocuous sigma, so sigma for softmax, is actually pretty complicated, because, well, in this graph, because I have a numerator which I need to compute, then I have a denominator which I need to compute, and then I need to divide the numerator by the denominator. So the simple softmax here in my computational graph ends up as being, a couple of operations. The matrix vector multiplication, if I wanted, I could break down even further. So if I want to do this in terms of single vector and matrix elements, then it would look like this. Yeah, so this is what I've abbreviated, what I have abbreviated on the left-hand side by this matrix vector product. I could also expand to be all of this, which we see on the right-hand side here. Okay. And now in this computational graph, it is relatively easy to apply the chain rule. So we start at the left-hand side, and this is, by the way, why I ingested the input on the right, so that my equations, which I write down, match the graph. I'm interested in the gradient of my loss with respect to the parameters W2, and the loss is again defined here. So you see that I have the multiplication operation here, which is why I need to use the sum rule. And I differentiate the loss with respect to t and t with respect to W2. But t was my target. This is the true class of my input x. And the true target, is just given by whoever gave me the training set. So it does not directly depend on W2, which is why this thing here is 0. It cancels. And then I have the derivative, the gradient of my loss with respect to the natural logarithm of O2, and then the partial of the natural logarithm of O2 with respect to W2. The first part I can evaluate. Yeah? So this is just minus t. It's the elements summed up, essentially. No, sorry, it's the vector itself multiplied with the identity matrix. And then on the right-hand side, natural logarithm O2 with respect to W2. I look at my graph. I see what this ln of O2 is composed of, and so on. So this is, I use the chain rule again. And this is all I do. Just apply the chain rule recursively. And an important realization is that, for example, this term here, I need it both when I differentiate with respect to W2, but also when I take the derivative with respect to W1. So that should remind us of dynamic programming, where we don't want to do redundant work. Yeah, we only want to do work if we need to do it at all. We want to do it just once. And this is why this partial derivative is like a message that can be sent along one edge of the graph. And these messages are kept until the bifurcation point. So everything that comes now on the right-hand side, I need only for the, excuse me, let me change colors here. So so everything marked in yellow, I need it for the derivative of both with respect to W1 and W2. But this part here, I now need only for the derivative with respect to W1, these messages here. Okay, so I'm sending messages back along my computational graph. And it is a good exercise to compute, the actual equations for a small example once. It can also be good if we have recurrent elements in our neural network, like the softmax function. Then it can make sense to combine these operations used in the softmax into just a single more complicated operator for which we can compute the gradient, and to maybe implement that low level in terms of programming. But in general, we now have the convenience that automatic differentiation will take care of all of this for us. Yeah? So when you do use a neural network in real life, then you specify the architecture, and then you simply invoke these auto-differentiation capabilities of your package of choice. Now, which is the package of choice? This changes very rapidly. So this time last year, most people in my lab, for example, use TensorFlow, and 1 year later, most everybody uses PyTorch, and so these fashions change relatively quickly. In this case, there's one of the reasons is that this computational graph in TensorFlow is built just once at the outset, and that allows the compiler to do a lot of optimization at the very beginning once, and then to profit from this optimization in an amortized fashion later. But in areas especially like natural language processing, where the input sentences may be of different length, or in computer vision, where we may get images of different size and so on, it may be more convenient to instantiate this computational graph dynamically, which is what PyTorch does. And to do TensorFlow justice, they also have found a means to deal with images of different size and so on, but it's not as natural as in PyTorch. Okay, so what is backpropagation in a nutshell? It is just the idea of using the chain rule as applied to a nested set of functions, which our neural network is, and to do computations just once and not repeatedly. So it's the idea of dynamic programming, essentially. And when applied to neural networks, this is called backpropagation. Then what if we want to compute derivatives not with respect to vectors, but with respect to matrices and such? Then we need generalizations of the Jacobians, and I'm referencing you here two nice write-ups. The first one is from the excellent Stanford course on neural networks, and the other one is by Eric Learned-Miller, and both walk you through all the stages from applying the chain rule on purely scalar nested functions, all the way to using this on tensors, so on matrices with more than 2 indices, and when we want to differentiate with respect to matrices with more than 2 indices. Good. Questions? Yes?
Here, for example, in this example, we use always ReLU in the intermediate layers and softmax in the end.
So why ReLU in the intermediate layers and softmax at the end? Is that the question?
Yes.
Okay, so for our target, it is convenient to map to the probability simplex. Yeah? So let's say if capital K equals 3, if I have 3 classes, then ideally I want my outputs So the first, so I have the output of my network. Let's say if it's a two-layer network, then I have two outputs. But now I could talk about the first neuron in the output layer and the second neuron in my output layer and the third neuron in my output layer. To require that they sum up to 1 and that they should all be non-negative. And geometrically speaking, this means for 3 classes that I want my outputs to live on this equilateral triangle here. And so I want something that maps my k outputs at this stage here. I get capital K numbers, and I now want to map this vector into this probabilistic simplex. And the softmax is a good way to do this. So it fulfills this normalization constraint, and it does give me non-negative numbers, and it is differentiable. So it does allow me to compute the gradient with respect to its inputs. This is why it's a good idea to use the softmax at the output. And in between, I need nonlinearities that are fast to compute and that do not saturate so easily. And the rectifying linear unit, it's for examples like this, it's very easy to compute its derivative, because if the activation was positive, then the derivative is just passing on the input. If it was negative, then the derivative passed on is 0. And it's just a frequently used activation function. More questions?
In this case, why all points is mapping to this specific simplex?
So the ground truth target is a unit vector. So it means the ground truth targets are either in this corner or in that corner or in that corner. And now I get a neural network output, and if I did not normalize my output, then my neural network output could be anywhere in this space. Like my output could be here, and let's say the ground truth tells me there. But now I would force the network to both learn the normalization, so both to bring it back to the plane, and then inside the plane to go in the right direction. But if I already know from the beginning that I want normalized, that I do want to predict either a corner or something between these corners, then I don't need to waste iterations and parameters to learn this normalization. I just impose it in the architecture of my neural network. So the softmax takes this point and projects it to this point in the triangle. And now inside this triangle, this has a convenient interpretation. It's just the closer I am to a specific corner, the stronger the network believes that this is the true class of the input. More questions? Okay. Yeah, go ahead.
Do I need to normalize also the features I need to the neural network?
Do I need to normalize the input to the neural network? No. The input can be anything. Okay, so there's much more to say about optimization. Like I said, choice of magic step size, which of the samples do we want to use to compute the gradient, all or only few. We will talk more about these choices. In the last few minutes, I just want to give you a completely orthogonal approach. Yeah? So everybody uses backpropagation. Nobody uses what I'm going to show you next. Why do I still show it? For two reasons. One is that it's not impossible that future hardware architectures may use this rather than backpropagation. And also just, to give you a bigger mental picture, to show you that backpropagation is not the only thing possible. Yeah? So this is the idea is nicely written up in this paper by Carrera-Perpignan and Wang. We again have a neural network with input X, and here the target is called Y. And shown here is the linear operation applied to X, and then we have the nonlinearity. And then the output of this, so to be a bit more precise, the output of this is then called Z1 from the first layer. And the output of the second layer is Z2. And the output of the third layer is Z3. Good. And they now propose the following, namely to introduce these intermediate variables or representations explicitly. And that means we need an intermediate representation both for each neuron. The neurons here are enumerated from 1 to capital K. So in my notation, capital K was the number of categories, but for them, capital K is the number of neurons. And moreover, we need one intermediate representation variable for each input sample, which here is indexed by small n. And so in a regression example where I use just, so this is just a squared loss. Here I want to minimize the squared residual between my ground truth output Y and the prediction of my neural network. And the prediction of the neural network is now defined recursively. So fk plus 1 is the prediction that I obtain by using the output z of the previous layer and applying this linear operator w. But the output of the previous layer is now defined recursively as a function of the intermediate variables in the previous layer and so on up to the very first layer. And if we enforce these constraints exactly, then I have an optimization problem over W and over Z. But this is equivalent to the original optimization problem, except that I have now many, many more variables. So I've not, I've only made my problem more complicated and not gained anything. However, instead of forcing these constraints exactly, and that's now a little bit similar to this dual decomposition idea that you saw in one of the exercises. Instead of enforcing the constraints exactly, I can just penalize any deviations from my constraints by adding these quadratic terms here. And if I minimize those quadratic terms, then the constraints will be satisfied if I minimize them exactly. And now I still have, a function of many more variables than I originally had, but it is a function which I can now optimize in a massively parallel fashion. And one way to do this is alternatingly, like in an EM algorithm, in the W step, I can fix my current internal representation variables and minimize just for the W's. And that means I need to find the optimum parameters only for each individual layer, which is a fairly simple operation. And then in the Z step, I now keep my updated parameters W fixed, and I only minimize over my latent variables z, which is just the solution of a linear system of equations. And this is what I try to indicate here on the right-hand side. So somehow, you can imagine that each input sample follows one trajectory through my network. And this trajectory I have here, this is really only a metaphor. I have represented by the set of particles connected by springs. And the analogy is fairly exact for the Z springs. So those are really just, I find them by solving a harmonic problem. But they are a bit of a metaphor for the W's because there I still have, the nonlinearities involved. And then I look to find an optimum for the system, and for different inputs, I will use the same parameters, but I will have different latent variables. And then I minimize jointly over all these latent variables and over all these parameters W. And this is much more similar to the kinds of problems that people have been solving in many body simulations and simulations of large particle systems, in statistical mechanics and in astrophysics and in all kinds of places, which is why there exist efficient codes and so on. Also, between iterations, there needs to be, of course, some. So let's say if we relegate each of these computations to one processor, then there needs to be some communication between these processors, but this communication is pretty local. It's always only between things or layers which are directly adjacent in this network. And this I can map to locality in my hardware, if I have a compute cluster. So I think this is a nice scheme, and I wouldn't be completely surprised if this did eventually catch on a larger scale. As it stands there, so I have a function with many more variables, but the function is not nested any longer. So I don't need to go through many iterations of the chain rule, and that could be an advantage. Any questions for this part? Yes?
If we define the Z recursively, are there any redundant computation existing in this architecture?
Are there redundant computations happening? If we enforce the constraints exactly, then all of these Z's are redundant, because then my network is just a deterministic function. But as we relax the constraints, this decouples it, in some way it's like unrolling the recursions in a deeply nested function. And then they're no longer redundant.
So by adding this penalty term?
Yes, by replacing the constraint with a penalty term. Okay. Yeah. Okay, so we have 2 weeks, I think, left until Christmas. And next week, I will talk about neural network architectures, so convolutional neural networks and specific architectures that make sense in the computer vision context, which operate on multiple scales and so on. And in the week after, I want to talk about the information geometry of gradient descent and why it makes sense to try and follow the natural gradient rather than the Cartesian gradient, and what that has to do with Fisher information, and how to compute that approximately for neural networks. No exercise this week because Sven is at NIPS, so we meet again Tuesday next week. Thank you.